Section 3.5, Continuity and End Behavior. Functions that can be drawn as a single line without picking up a pencil are continuous. Functions that have gaps, jumps, or asymptotes are discontinuous. There are three types of discontinuities. An infinite discontinuity is when your function goes to positive or negative infinity as x approaches some number. This is a vertical asymptote. So here's an example of an infinite discontinuity where your vertical asymptote is the y-axis. So as you approach the y-axis, as you approach x equals 0, your function goes to infinity but never actually hits x equals 0. The function is not defined for x equals 0. Jump discontinuity indicates that the graph stops at a given value of the domain and then begins again at a different range value for that same value of the domain. So here you have a jump discontinuity because the function has one value, so it has one value going up to 0, and then from 0 on it has a different value. So for a jump discontinuity, the function may or may not be defined at the discontinuity. And then point discontinuities occur when there's a single point that is not in the domain, but the ends match up. So you have a point here where the function is not defined, but it's defined on both sides, and the ends match up. That's called a limit. You would say that the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. You will talk about limits extensively in calculus. We have 3 rules to test for continuity. A function is continuous at some point x equals c if it satisfies these conditions. The function is defined at c, which is to say f of c exists. The function approaches the same y value on the left and right sides of c, and the y value the function approaches from each side is equal to f of c. This is literally just limits. When you do calculus, you'll be like, oh, I remember that because I learned things in Miss Schumann's class. So for A, right, step 1, is the function defined at x equals 1? Can we plug 1 in here? So 3 times 1 squared plus 7 is 10. So pass step 1. Does the function approach the same y value on the left and right sides? So if I pick x equals 1.01, right? So like if I pick something 1.1, say, and plug that in, am I going to get something close to if I pick something a little bit less than 1? So 1.1 squared plus 7 is going to be 1.21 times 3 is 3.63, 10.63. Whereas if I plug in 0.9, I'm going to get 0.81 times 3. Now 0.81 times 3, which is 2.43, plus 7, which is 9.43. So, function appears to be approaching 10 from this side, appears to be approaching 10 from this side. So approaching the same number from both sides, and is that number equal to this number? Yes. Passes all 3, so this is continuous. For B, step 1, can we plug in x equals 2? So f of 2 would be 2 minus 2 over 2 squared minus 4, which is 0 over 0. Function is not defined at 2. So, fail step 1, this is not continuous. For C, is the function defined at x equals 1? If we plug in 1 here, do we get a value? Yes, right? 1 is in the domain, so we pass step 1. Step 2, does the function approach the same thing from the left and the right sides? So as 1 over x, if I plug 1 in here, I'm going to get 1. And if I plug 1 in here, I'm going to get 1. So, approaches 1 from both sides. And if is that thing, the thing that it approaches in number 2, equal to what it's equal to in number 1? Yes, they're both 1. So, passes all 3. This is continuous. A function is continuous on an interval if and only if it is continuous at each number x in the interval. Polynomials are continuous for all real numbers. That's very handy. Rational functions often have infinite and point discontinuities, and piecewise functions often have jump discontinuities. On January 10, 1999, the United States Postal Service raised the cost of a first-class stamp. After the change, mailing a letter costs 33 cents for the first ounce and 22 cents for each additional ounce or part of an ounce. The graph summarizes the cost of mailing a first-class letter. So, stair-step functions like this are called discrete functions. For discrete functions, you can't, your function only takes certain y values and doesn't have y values in between those. So here, your function can only be, your cost of your letter can only be 33 cents, or 55 cents, or 77 cents, or 99 cents. It can't be anything in between those. So that would be a discrete function. Use the continuity test to show that the step function is discontinuous. So the function is defined for all, first ounce, right? So the function is defined everywhere, but so that passes 1. Step 2, it does the limit as we approach a point from the left-hand side. Is that equal to approaching it from the right-hand side? And we need to show that that's true for all points. Or we need to find a point, like here at x equals 3, where the y value as we approach it from the left-hand side is different from the y value as we approach it from the right-hand side. So at 3, or at 2, or at 4, etc. At any whole number x value, our function is discontinuous as it fails step 2. Why would a continuous function not be appropriate to model postage costs? Well, we can't have fractions of pennies, right? A continuous function would have to take all y values, and so then we would have to possibly have a letter that weighs 3.179283 ounces, and we would have a price in dollars that would be, 0.1 $0.794382. And we can't do that. We can't have a fraction of a penny. So it would not be appropriate to have a continuous function because continuous functions have to take all values in the interval. The end behavior of a function describes what happens to the y values as the x values become infinitely large in either the positive or negative direction. So we always say as x approaches negative infinity, so that's going to be talking about the left-hand side of the graph. So what does this function do? On the left-hand side of the graph, the function f of x approaches infinity. If it goes up, it approaches infinity. For the right-hand side of the graph, we say as x approaches positive infinity, what does the function do? And so this one's also going up, so that's f of x approaches infinity. So I can go ahead and write this part, because this part is always going to be the same. We're describing the behavior as x approaches negative infinity, which is the left-hand side, and positive infinity, which is the right-hand side. And as x approaches negative infinity, f of x approaches what? And as x approaches positive infinity, f of x approaches what? So this function on the left-hand side, as we go to negative infinity, our function goes to negative infinity. And on the right-hand side, as we go to positive infinity, our function goes to positive infinity. It goes up. This function, as x approaches negative infinity, so the function is not going to infinity. It's not going up or going down. It's flattening out. It approaches 0. And same thing on the right-hand side. The function isn't going up or going down. It's flattening out. So this, we'd say f of x approaches 0. So that is a horizontal asymptote. So, in general, the end behavior of a polynomial depends on the degree of the function and the leading coefficient. So, if the degree of a function is the biggest exponent in the polynomial, so if the biggest exponent is even and the leading coefficient is positive, the leading coefficient is the number in front of that biggest exponent. So if the degree is even and the leading coefficient is positive, then your end behavior is going to approach infinity on both ends. So as x approaches negative infinity, f of x approaches infinity, and as x approaches positive infinity, f of x still approaches positive infinity. So this would be, for example, something like f of x equals 3x to the fourth plus 8. I don't know. This is not at all a good graph of this example function, because it doesn't matter what weird wibbly stuff the function is doing in the middle. We're only looking at the ends. So even exponent, positive leading coefficient, both of the ends are going to point up. If we have an even exponent and a negative leading coefficient, both of the ends are going to point down. So as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches negative infinity. Both ends point down. An odd exponent, if the leading coefficient is positive, is going to have n behavior that go in opposite directions. So if the leading coefficient is positive, as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. It goes up on the right-hand side and down on the left-hand side. Negative leading coefficient is going to be the opposite way. So as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. Describe the end behavior of each function and sketch an approximate graph. So for A, x cubed plus 2x squared plus x minus 1. And when I say approximate graph, we're going very approximate here. I don't feel like actually picking numbers and plugging stuff in, so very approximate. The degree is 3. The leading coefficient is 1, positive 1, so it's going to be as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. So it maybe looks like that. I don't know. Our degree is 4. And our leading coefficient is -2. The leading coefficient is the coefficient, the number in front of the biggest power, even if it's not written so that it's technically leading. So even degree means that both ends of this function are going to point the same way. Negative leading coefficient means that that way is going to be down. And if I were going to be really careful with this, I would plug some numbers in and plot some points, but I'm not. All I care about here is the end behavior. Here, for C, this is not a polynomial. This is a rational function. And we will talk about the rules for rational functions in the video for 3.7. But right now, the degree, the fact that the numerator and the denominator have the same degree means that we have a horizontal asymptote, and that horizontal asymptote is going to be at 1. It's the ratio of the leading coefficients, and your leading coefficients here are both 1, so you're going to have a horizontal asymptote at 1. We also have a vertical asymptote at 2, because that's where the function is undefined, which means that our function is going to look like this. And like that. So for C, we would say as x approaches infinity, or let's start with negative infinity, f of x approaches 1, and as x approaches positive infinity, f of x approaches 1. Intervals of increasing decreasing are judged viewing a graph from left to right. So from this end going this way is decreasing, going this way is increasing. If a function is strictly increasing or strictly decreasing on an interval, it's said to be monotonic. Graph each function, determine the intervals on which the function is increasing and the intervals on which the function is decreasing. So use our transformation rules, right? So this would be negative x minus 5 squared plus 3. That's going to be the graph of x squared. It's going to be shifted 5 units to the right and 3 units up, and that negative out front means that it opens down. So it's going to look like something like this. Right? So the function is increasing on the interval, right, on this part. So it's increasing on the interval from negative infinity, so all the way to the left, all the way up to 5, and it's decreasing on the interval from 5 to infinity. From 5 infinitely to the right, it is decreasing. B, 1/2 absolute value of x plus 3 minus 5. This is an absolute value function. Transformation rules again. It's shifted 3 units to the left and 5 units down. It opens up, but these are going to have, the sides are going to have a slope of 1/2 instead of a slope of 1. It's flatter. So for B, the interval where it's increasing is, it is increasing from -3 to infinity, and it's decreasing from -infinity to -3. Our intervals of increasing and decreasing are always written in terms of the x values. And our last one is a cubic function that I don't want to graph. If I plug in 1, it's got to have something here. If I plug in 1, that's 2, 6, 2, 5, 8, -4. You know what? I'm going to have Desmos help me out on this. Bear with me here. It's been a long day. So 2x to the third plus 3x squared minus 12x plus 3. And so we've got, oh boy, that one goes way off the graph. So you've got a point that is at -2 and +23. So way up there. This point at -1, or at 1, -4 is a minimum. We hit, let's see, 2 is going to be 7, 3, 4, 5, 6, 7. And we have a 0, another 0, like here. So the function ends up looking something like this. Okay, so the interval, it is increasing on the interval, and you can't really see that. It is increasing on the interval from negative infinity to negative 2, and also from 1 to infinity. And it is decreasing on the interval from negative 2 to 1. And that's it. Make sure you study for your test. That's coming up next week.